Okay, welcome back. So from now on, I'm just going to do some quick videos about some basic cycles. So the first one is the Rankine cycle. So what is the Rankine cycle? Rankine cycle is for any type of a steam machine vapor power plant is basically the fundamental cycle that is used. So let's just write it down. So the Rankine cycle is the building block for any vapor power plant That's it. I think that's all we can do. So basically, if it's the ideal cycle or the building block, we should be able to sketch the cycle on a TS diagram. Okay? Now, let's see. What do we need in order to have, let's say, a steam machine, or also a vapor power plant can be a nuclear plant that you just use nuclear energy to boil water. So what we need is what? We need a boiler. So it should be maybe the first component. What else do we need? So the boiler, so if we need water to put into the boiler, but we're going to need a pump to pump the water into the boiler. So we pump water, it goes up, we put into the boiler, we boil it. We're going to put this into a turbine that would generate the power. Okay, and now we just need to close the system. So we need to put over here a condenser. So basically the water comes very hot over here. You need to cool it, pump it again, and we go over and over. So if we start from here, so we have 1, 2, 3, and 4. Okay. So over here we're gonna have this figure over here. All right. So let's say we start from the water as state 1. So the water is gonna be at a certain pressure, and on the ideal case, the best state will be to be what? Will be to be saturated liquid over here. This could be 1. So this water will be at a certain pressure, P1, and it will be the atmospheric. So if we do a dotted line, maybe I can just do a full line, would be over here. Because we go through the pump, you're going to have a small increase in pressure. Generally it's very small. I'm going to do it much bigger here just for the figure. And this will take the water into a second line of power over here, P2. So this will be right after the pump. We get here 2. Now the water is going to get into the boiler. So what's going to happen in the boiler? You're going to heat it. It's going to go to saturated water over here. It's going to still be heated, and the minimum temperature you need would be the water to be here saturated vapor. But you will see that in most cases the water will keep going up. Maybe that figure is not that good. Not good at all. But I mean, anyway, it will still be going up over here. We'll see that in another video. And then if you don't have any loss into the turbine, 3 to 4, that means that the system is isentropic. You will be going through a straight line. And you will be going here to 4. And you can close it over here. So basically, the ideal cycle is this one. What I'm just trying to say is that in most cases, you can overheat the water, and then this will drop here to the line of the same pressure, but I cannot put it over here. So I will say that on another video. That's not a problem. So in order for this to work, what do we need? So let's see. On the condenser, to boil the water, you need to put some heat in. Okay? On the condenser, you're going to have some heat that will be coming out. Okay? Now, the role of the turbine is to do what? To generate power. So you have some power out, but we'll have to put some power into the pump to make it work. Okay? So the next page I'm going to give a very quick explanation of what happens on each process. So let's see, processes, and here I'm going to put 1, 2, 2, 3, 3, 4, 4, 1. So what happens in process 1, 2 is an isentropic compression. It's a very small one, but it's still an isentropic compression. You assume the ideal pump, and you're going to compress a little bit the fluid to a higher pressure. So basically, P2 is just a little bit higher than P1. Now, 2 to 3, you have a constant pressure process. The pressure is P2. And what do? You go through the boiler, so constant pressure, heat addition. Okay, basically, let's go back. 1, 2, you increase a little bit the pressure. 2, 3, you go through the boiler, constant pressure, heat addition. Process 3, 4, now you go through the turbine, and they say an ideal turbine, so it's an isentropic. You go from a higher pressure to a lower pressure, so that's an expansion in turbine, so you generate power. And finally, for the process for 1, what are you doing? You heat rejection, if you want, in the condenser at constant pressure. So if you want, will be constant pressure, heat rejection. So this happens in the boiler. This will be in the condenser. Okay? So you see it's not that complicated. But basically on the figure, so let's see. This is the page we just created. So maybe we can add a few things here. Let's see. 2, 3, you'll be adding the heat over here. 4, 1, Q out. Might be too much information, but I don't know. We might be able to make it work. Now, process 3, 4. Not sure about what color to use, maybe the black. Here's the one that you generate the power out. and on the 1, 2 here is when you need to put the power in. Okay? Okay. So now, the amount of power, so let's look at the power of work that we need to put in. So we know that the pump is going to require power. So pump is the one that is in. Okay, I put it here. This generally will be equal to what? If you look at the figure, pump should be equal to H2 minus H1. So let's say this is in kilowatts, so it will be M H2 minus H1, and this will be the mass flow. But in most cases, you know that all these values will be per unit mass, so the power will be H2 minus H1 per kilogram in most problems. And the amount of power that is out is at the turbine. So this will be the mass flow of water. So what would that be? According to the figure, should be H4 minus H3. Okay, and you can find all these as using the tables. Could be the power. Now let's see about the heat transfer. So what do we have? The Q in is in the boiler. And this would be equal to what? M H3 minus H2, and the Q out is in the condenser, and that should be equal to M H1 minus H4. So there's really nothing new. Here, the only thing I'm going to add is that in the pump, you can do it with H2 and H1, but sometimes you need to do the approximation of M will be equal. So what happens in the pump? We know that there is a certain increase in pressure, and this could be TV, but the volume is almost constant if it is an ideal pump. So this is equal to M P2 minus P1 times the volume of water going through it. You can also approximate it that way. Okay, I just want to add one little thing over here because of our sign convention. Basically, that states that any heat going in is positive, any heat coming out is negative. But for work, if you remember, is reversed. So any work coming in is negative or power, and any work or power coming out will be positive. So if you look over here, what is happening really over here, let me use the red, is that if you look at the power out, will be between 3 and 4. So H3 should be higher than H4. So if H3 is higher than H4, it will give us a negative value. So again, if we don't want to make any mistake, rewrite this as M H3 minus H4. And we have to do something similar for the heat, for the Q out. So the Q out here we have H1 and H4. So H4 will be hotter, so we'll have more enthalpy than H1, meaning that this, so the other way around, sorry. So over here we need to do a similar correction. We need to do m. If you just want to use the magnitude and not the negative of the negative, just do over here m h4 minus h1. You don't have to do this really if you still remember the sign convention, but to keep everything in positive will help us on the next step when we need to calculate the efficiency. So what would that be? This would be the efficiency of the Rankine cycle. So by definition, what is the efficiency? Is whatever we're trying to get out, which is the net work, divided by whatever we need to put into the system. So if you think about it, what you need to put in will be equal to the power generated by the turbine minus the power consumed by the pump divided by the Q in put into the boiler. So now we just substitute. One way to calculate efficiency will be to do what? So the one of the turbine will be m h3 minus h4 minus the one of the pump would be, so we can use either m h2 minus h1 or the other expression of m divided by the one of the boiler, m h3 minus h2. So one first expression for the efficiency would be equal to what? h3 minus h4 minus h2 minus h1 divided by h3 minus h2. So this will be the efficiency for an ideal Rankine cycle. Okay, another way to do this, I'm going to do it very quick, that will also work, is by definition what is also the efficiency we know is the net work over Q in, but really this would be equal to Q in minus Q out divided by Q in. All these are heat transfer of power is the same. So at the end we get 1 minus Q out over Q in. And this, if we look at the equations from the previous page, will give us what? 1 minus Q out would be m h4 minus h1 divided by m h3 minus h2, or what is the same, 1 minus h4 minus h1 divided by h3 minus h2. So this should give you the same result as the previous expression. Okay, so this is the efficiency for the ideal Rankine cycle.